Topic 8-4, referenced in our Holt textbook, Chapter 7, Section 3, page 470 and 477. These theorems and postulates can be looked at individually. I actually have a chart you can ask me for to go along with these topics. Another one I want to plug again is mathisfun.com. You can look at similar triangles, and it shows lots of examples of these types of similarities in the theorems and postulates that go along with it. So again, for the third time, we're going to write down what makes a polygon similar. They have to have two criteria. One is that the corresponding angles are congruent, and second, the corresponding sides are proportional. If you don't know the measures of all the sides, there is another way to tell. These are several theorems that will allow you to prove triangles similar. So again, look up in your textbook or on the internet. The mathisfun.com are good to show some good examples of how these theorems were derived. The first we're going to look at is angle-angle. As long as you have two triangles that show two angles, corresponding angles congruent, then the two angles of another triangle would also be similar if they're showing to be congruent. So here you only need two things, two angles that show congruency. That's why they show it with a big A and another A, AA similarity. So if we're trying to classify these to be proven similar by AA, we're going to write the similarity statement. Again, be careful to note the similar to similar. And I'm going to use highlighters to help do this. The A corresponds with the D. The B is the right angle, so it would correspond with the other right angle. And then E is similar to E, can be just shown like that. Okay, so when you're naming similarity, they've already shown to you, the box shows 90-degree angles on both, and then these are both showing congruent by vertical. Those are vertical angles. Therefore, it can be proven by angle-angle similarity, but just make sure you name it in the same way. If I start with the pink, orange, yellow, I'm going to say pink, orange, yellow. ECA is similar to triangle EBD. Okay, so there are things that you can show proven. Vertical angles, even if it's not marked, you can mark it. Any two lines cross, the opposites are congruent by vertical angles. This J and this F, if they've already shown you with this little arrow that JK and GF are parallel, then these two are congruent by alternate interior angles. And you can also show that K and G are congruent by the same thing, alternate interior angles. Therefore, all you've got is two similar angles, two congruent angles, therefore the similarity is AAA. But if you wanted to show it by, you got to be careful, this K is not similar to the F, it's similar to the G. Likely, of course, the H is similar to the H, and the J and the F are similar. So if it helps, grab some highlighters to mark similarities. So again, when we name it, you have to do it in the same order both times. Triangle JHK is similar to triangle FHG, starting both times with yellow, orange, pink. Yellow, orange, pink. You wouldn't say it's similar to GHF, even though it's a triangle. You've got to name the similarity because that shows congruent parts. Proportional parts. Okay. Continuing to use highlighters for when they're wanting us to find certain parts. There's a lot going on in example 2, so label, label, label. Make sure you label things. The first one is showing these two bracket lines show parallel. Notice we show that with arrows along the sides. So if AB is 4, we label that 4. AE is 3x plus 1. ED is x plus 12. They want us to find what these are, so I highlighted it. We want to know what AE is and what this is. These are congruent. We can mark them by vertical. These are congruent by alternate interior angles. You've learned two parallel lines cut by a transversal. This one and this one are congruent. So we already know that they're similar by angle. Now let's show what these actual values would be, since it's only shown in an expression. You don't necessarily have to find the scale factor for this. You could just set up the proportion, but we can reduce it. Instead of using 4 and 8, we can use 1/2, because 1/2 reduces to, 4/8 reduces to 1/2. So you can show that 1 is to 2 as the 3x plus 1 is to the x plus 12. This is to this as this is to this. Alright, they've shown the distribution, cross products, come down, solve, till you finally get 2. Be careful. Make sure you don't just say the answer is 2, because they're not wanting the solving for x. They want you to actually solve for this side length. So you have to actually plug in a 2 for x and add 12 to get 14. Plug in 2 for x, multiply by 3, and add 1 to get 7. So that's where they came up with these. Okay, another way, another theorem is a side angle side similarity. Now what's important about this is the angle has to be inclusive inside the two sides showing to be congruent. So the angles are proportion, and then the triangles are similar. The sides included in the angle. So we always have to know that the angles are congruent and the sides are proportion. So again, notice where this A is. It's in the middle. Side, angle, side, side, angle, side. So in this example 3, can we determine whether these two triangles are similar? Well, the angles are definitely the same. So, or do the sides show proportion? Is 4 to 6 the same as 6 to 9? Cross product proves that they are. So yes, it is by side, angle, side. Side, angle, side. Again, naming it's important. If I start with an MNL, I have to start with the P because it corresponds to the same similarity. PRQ. Alright. Another theorem is the side, side, side. If all three pairs of corresponding sides are proportional, then the two sides are congruent. So in this triangle, we're trying to see if 3 is to 9 can be reduced to 1/3. So 1/3 is our scale factor. So we can try our cross products with everyone showing. 4 is to 12, 5 is to 15. All of them would show congruency. 9 to 9, 15 to 15, with cross products 12 to 12. Therefore, they are congruent. These have triangles inscribed inside of another triangle, but you have to realize that this triangle shares a common angle with the smaller triangle. So we're trying to prove how would be angle, angle, because we've already proven these two to be the same. And if this is a shared angle with both triangles, then you can prove them to be congruent by angle, angle similarity. XWV, notice how they started with the X. WV, you would start with the X again, going to the same side and then out. Make sure you name them in the correct order. That's important. Okay, another one here is that this is showing this whole length, and the whole entire side from J to L, you have to see that, is a 9. It's likely, same thing, this whole side from L to N is 15. So when they're showing the similarity, the 6 is to, compared to the big triangle, 9 as the 10 to the 15. Both of them get the same scale of reducing to 2/3. Therefore, you've got a side angle, side, side, angle, side. It's a little confusing because they're inside of each other. If you want to, draw them separately. But KLN, starting with the K, you're going to start with the J, which is similar to JLN. Okay, this one's a little bit tricky. Notice how it's shown similar to similar. They flipped this. It's not only, it's turned around. This short side is the same as this short side. So that's representative with boxes. This longer side is 5, so it corresponds with this longer side. Be real careful because it's this similarity to EF similarity. So EF is 12. 6 is to 12, 5 is to 10, 3 is to 6. Do we get the same scale? Yes. Why would this be similar? Side, side, side. In naming it, if you started with E, D, G, be real careful. You've got to start with the, notice how this is the short side, or I'm sorry, this shorter angle. This has actually been flipped. So that one corresponds with that one. The D corresponds with the H, and the G with the G. So notice, wait a minute. It actually, this one ends up becoming the same. For one, it's used as a short, but for the big one, this is actually representative with both. So you start with E, D, G. So you're going to start with F, H, E. Because notice how this shared angle right here is with this one. I guess I should show it like that. That one's the orange when it becomes the larger triangle similarity. But when you're with the smaller one, it's represented with this one. Color code if necessary, if it helps. Okay, last two examples. First, you want to find the scale. If you're looking at the similarity, notice that it's a triangle inside of a larger triangle. The smaller triangle and the larger triangle share the common angle C as congruent, and it's shown that these two are congruent. So you have to look at the larger triangles alongside as 3 plus x. So this shorter side 3 is to the longer side 3x, as our scale is 4 to our longer side 7. We just added those two together. When you take your scale along with the unknown, we can solve for x. This 7 times 3 is 21. Do the distribution, you're going to get 12 plus 4x. Subtract 12 on both sides, you get 9. Divide by 4 and you get 9/4. So 9/4 is what x would be, which is this one. And if you need to solve for y, you know that 4/7 is your scale factor. So using 4/7, y is to 8. And always going from the small scale to the large scale, small triangle to the larger triangle proportionately. 28, 7y, I'm sorry, 32, 7y, divide by 7 and you get a fraction. You want to leave it as a fraction. The last one, if we want to find the scale, again, remember when we did this with the sides, well, they just drew it. 4, 5, 7. The measures of the others are 16, 20, 28. Keeping the smallest, the middle, the large, small, middle, large. Labeling it as such, the same corresponding AB would be the same as XY. First, figure out the scale factor. 4 is to 16 is 1/4. So each time you can compare each of your proportions to 1/4. And if you do, yes, is similar triangles. This one, however, a 3, 5, 6, and be careful, they didn't name this in the right order because 2 is your smallest number. So you would want to make sure you name that along with the 3. 3 and the 2, 5 and the 2.5, 6 and the 3. Notice if you try to scale the 3 with the 2, that's going to be 3 halves. But if you scale 5 as to 2 fifths, it's not going to be the same scale. 6 to 3 is 1 half. So none of them match up with the scale, so this one would not be similar. And we'll be going through some other examples, but that is it for topic 8-4.